Two impossible forces hit Earth within 72 hours. A G3 geomagnetic storm on September the 15th knocks air traffic and power grids into emergency mode. By the 18th, a magnitude 7.8 earthquake shakes Kamchatka, hours after interstellar comet 3I/Atlas surges toward closest approach. The official line says these events are cosmic coincidence, aftershocks following tectonic law, solar storms nothing new. But the raw statistics of this convergence and whispers of electromagnetic triggers refuse to stay buried. What if the biggest threat isn't just nature's chaos, but a hidden mechanism linking space and the planet's crust? Is 3I/Atlas causing earthquakes on Earth? And we're about to test the line between proven science and the unthinkable. A G3 geomagnetic storm is not a routine solar hiccup. On September 14, 2025, solar wind raced outward from a vast coronal hole at over 700 kilometers per second, twice the average speed of the solar wind on a quiet day. This torrent of charged particles slammed into Earth's magnetic field, compressing the magnetosphere and setting off a global disturbance that space weather forecasters measured with the KP index. KP7 means strong. Only a handful of storms each solar cycle reach this threshold. Unlike the dramatic, sudden punch of a coronal mass ejection, this event was driven by a persistent high-speed stream. On July 29, 2025, the Kamchatka Peninsula experienced a seismic rupture of rare intensity. An M7.8 earthquake tore through the offshore fault system, releasing decades of accumulated stress in a matter of seconds. On September 18th, a magnitude 7.8 aftershock struck just south of the July epicenter. The field evidence, dense and precise, would fuel debates about what, if anything, could nudge such a system toward failure. Unlike solar system natives bound by elliptical orbits, 3I/Atlas traces a hyperbolic path through space, a trajectory that guarantees it will never return. Its orbital eccentricity exceeds 1.0, a mathematical fingerprint that confirms its interstellar origin beyond all doubt. Yet, 3I/Atlas is not just a mathematical curiosity. As it hurtles toward perihelion on October 30th, its physical profile defies expectations. The coma, an immense, diffuse envelope of gas and dust, extends hundreds of thousands of kilometers, dwarfing the nucleus within. Most comets remain dormant until much closer to the Sun, but 3I/Atlas began venting carbon dioxide at distances where solar heat is weak. Spectroscopic analysis reveals a CO₂-rich chemistry with traces of cyanide and atomic nickel, unlike the water-dominated coma of typical Oort cloud comets. Its extreme negative polarization and forward-brightening morphology have electrified the astronomical community, hinting at grain properties shaped in alien environments. Despite the spectacle, 3I/Atlas poses no threat to Earth. Its closest approach, projected for mid-December, will keep it 1.8 astronomical units away, well beyond Mars's orbit, and far outside any gravitational or physical hazard zone. The object's passage is a scientific gift, not a menace. For the Atlas astronomers, the real story is written in spectral lines and orbital plots, not doomsday headlines. October 2025 offers a rare spectacle, not one, but a cluster of bright comets threading the inner solar system. C/2025. R2 SWAN sweeps past Earth at just 0.26 astronomical units, close enough for its ultraviolet emissions to be tracked by the SWAN instrument. This proximity turns the comet into a natural plasma probe, its tail reacting in real time to solar wind gusts and magnetic field reversals. Each twist and disruption in the plasma tail encodes a record of space weather conditions that satellites alone cannot capture. C/2025. A6 Lemon, forecast to brighten to magnitude 8 or 9 in early November, brings another point of comparison. Its coma, rich in water and cyanide, responds differently to solar activity than the carbon dioxide-driven envelope of 3I/Atlas. Earlier in September, K1 Atlas reached its own peak, providing baseline data for how Oort cloud comets behave during periods of heightened solar wind. The timing of these apparitions, each with a distinct origin, composition, and heliocentric distance, creates a multi-point laboratory for heliophysics. For researchers, this swarm is more than a celestial coincidence. Plasma physicists and mission planners from ESA's SWAN project coordinate with ground-based observatories, leveraging the diversity of comets to cross-check models of tail formation, ion pickup, and magnetic reconnection. Dr. Elena Mazzoni, a SWAN mission scientist, describes the opportunity as a living experiment in solar wind, comet interaction unfolding across millions of kilometers. The data gathered this month will shape our understanding of how charged particles sculpt cometary tails, and by extension, how the sun's invisible hand reaches deep into the solar system. Debate over electromagnetic earthquake triggers begins with a deceptively simple idea. Can a geomagnetic storm, acting through Earth's ionosphere and crust, nudge a fault already balanced on the edge? Some researchers point to the so-called vacuum trigger hypothesis. When the solar wind density drops during a high-speed stream, the local plasma environment thins, creating conditions where electrical currents from the ionosphere to the ground can flow more freely. In theory, this might focus energy into conductive fault zones, especially if the fault is already critically stressed. Dr. Elvira Kuipers, a geophysicist at Utrecht, has spent years dissecting these claims. Her analysis draws a sharp line between physical possibility and energetic plausibility. During a strong G3 storm, the induced electric fields at Earth's surface rarely exceed a few volts per kilometer. Fault zone conductivities, measured in the field, range from 0.01 up to 1 Siemens per meter. The resulting current densities, on the order of microamperes per square meter, fall short by many orders of magnitude. To trigger slip on a major fault, the required shear stress is at least 1 million times greater than what these currents can deliver. The energy budget is equally unforgiving. Joule heating from geomagnetically induced currents, even under peak storm conditions, raises local temperatures by less than 1/100th of a degree Celsius. Laboratory experiments on simulated faults confirm this. No measurable weakening occurs at field-relevant current strengths. Reverse piezoelectric effects in quartz-rich rocks, another proposed pathway, generate strains so small they vanish into the noise of tectonic stress. Electro-osmotic flows, where electric fields drive fluids through fault gouge, change pore pressures by less than a single Pascal. Yet the threshold for triggering a quake sits thousands of times higher. Kuipers summarizes the consensus. If a fault gives way during a storm, it was already at the breaking point. The storm is, at best, a feather landing on a loaded scale. Statistical studies occasionally find a hint of clustering between storms and seismic activity, but the physical mechanisms remain stubbornly out of reach. For now, the vacuum trigger and ionosphere crust coupling models remain intriguing, but the numbers keep them firmly in the realm of speculation. At sunrise on September 17, 2025, Mercury crossed directly between Earth and the Sun, a moment of perfect alignment calculated to the minute by JPL's ephemerides. For planetary alignment theorists, this conjunction is more than a calendar quirk. Some propose that Mercury's position can subtly reshape the geometry of the heliospheric current sheet, the vast undulating plane of solar magnetism that Earth swims through. The argument is not gravitational, Mercury's pull is negligible, but electromagnetic. Theorists point to sector boundary crossings in the interplanetary magnetic field, noting that Earth encountered a negatively polarized sector just as the high-speed solar wind stream arrived. In their view, such timing could, in principle, modulate the way solar energy couples into Earth's magnetosphere and ionosphere. Yet for every advocate, there is a skeptic armed with numbers. The heliospheric current sheet wobbles with or without planetary alignments, and the scale of Mercury's influence remains, at best, a curiosity, no more than a rounding error in the equations that govern solar wind propagation. A different minority voice looks not to the sky, but to the other side of the world. The antipodal hypothesis suggests that seismic waves unleashed by a major earthquake can travel through Earth's core and mantle, focusing energy at the planet's opposite point. In theory, this could nudge distant faults closer to failure, creating a global echo of the original rupture. Historical case studies, like the 1994 Bolivia quake, have recorded faint microseisms near antipodal zones, but only at magnitudes far below damaging levels. Quantitative analysis reveals the problem. More than 99.8% of the wave energy dissipates before reaching the antipode. For a Kamchatka scale event, the ground motion at the antipodal focus is measured in fractions of a millimeter per second, insufficient to trigger anything beyond background noise unless a fault is already poised on the brink. Mainstream seismologists find no statistically significant uptick in large quakes at antipodal points, even after the most powerful events of the past decade. Both alignment and antipodal theories share a common thread. They capture the imagination precisely because they reach for patterns at the edge of physical plausibility. Each offers a way to connect distant events, a planet's fleeting shadow, a wave's silent journey, with the drama of seismic release. Yet beneath the speculation, the numbers remain stubborn. For now, these ideas live in the margins of scientific debate, reminders of how far curiosity can stretch when confronted by cosmic coincidence. On September 14th to 15th, 2025, a G3 geomagnetic storm with a 700 km per second solar wind and KP7 conditions disrupted aviation and power grids worldwide. Just 4 days later, Kamchatka experienced a magnitude 7.8 aftershock. The interstellar comet 3, I/Atlas, confirmed by its hyperbolic orbit and carbon dioxide-rich coma, passed safely at over 1.4 astronomical units from Earth. Seismic records and Amori decay models place the aftershock squarely within expected tectonic patterns, and USGS documents cite no proven link between geomagnetic storms or comet passages and earthquake initiation. However, published studies on ionospheric disturbances, planetary alignments, and antipodal effects continue to explore possible but unconfirmed electromagnetic triggers, especially where faults are already near failure. Ultimately, the 2025 cosmic convergence highlights the importance of separating measured facts from debated mechanisms, even as the search for deeper connections continues.